Today I'm going to be talking about how models can adapt and work in the wild, right? If we go to new areas, go out camping, we might see different conditions, like this beautiful sunny landscape, or maybe less beautiful weather, like snow or storms. And what I'm going to talk about today is this direction of test time adaptation. Is this mic not working? Ah, sorry. Can everyone hear all right? Okay, thank you. All right, so that's the kind of adaptation we need, right? We might have a wrong condition and we need things to update, like me turning on the mic. I want models to be able to keep trying and update if something in the data has changed or is wrong. So let's get to how we might be able to do this. The problem, as I just outlined, is that the data can change, right? Shift happens. Here I have all these kinds of images, right? And each one has its own kind of shift or corruption. Shift meaning that the data has changed, right? There are cases of noise, like Gaussian noise, that we might have from some electronics issue. There are cases of blur, like we might have from motion or having things on our camera lenses. Or for instance, types of weather, like I mentioned, right? We might see snow or ice or fog. And last, there might be kind of image compression issues, right? We have digital images. We might have compressed them aggressively for storage, but now our models might not do as well on these compressed images. So what I would like is to figure out how can we take the error that we get on all these shifts. Here, the red line, almost 60% error on all these kinds of shifted data for a model that should be getting 24% error on its normal clean data, right? This is almost tripled the amount of error. And these aren't such intense changes, right? I think you can all see that all these images are still a bird, yet our models can't. So I'll argue the issue is that our testing data, the data we deploy our model on, can change in so many ways. But standard models all stay the same, right? We have the same parameters, the same model on every input. And this can mean that the models don't generalize, like we see these kinds of errors here. So how could we equip a model to actually keep calm, carry on, and adapt along with each of these new shifts? Because there will always be more shifts. You might have seen in the news some time ago, there were wildfires in California, and suddenly everything was orange, right? This is not something we train for. When a shift like this happens, we even have to just collect this data, much less label it and retrain a model. So there's a gap there where our model might be wrong. And this happened throughout the Bay Area. And I would argue that this kind of shift and change is actually normal. It's less common for our data to stay perfectly the same, right? The world changes all the time. So how can we get a model that, seeing one of these strange wildfire landscapes, can still try to do its best and do more than it learned during training? So what I'm talking about there, just to categorize these kinds of shifts, is a natural shift, right? Like the weather. This changes the input, as we see in this snowy scene of Yerevan, but it changes the input in a systematic way, right? There's snow in every image, and the snow looks similar across the images. In contrast, there are also what are known as adversarial shifts, right? These are attacks that actually act like an opponent, as you would in a chess game with all these vernissage chessboards, that are trying to make your specific model wrong, right? There's a different kind of shift because they're against your model, not just changing all of the data. So to start, I want to look closely at, one, how can models adapt to these natural shifts? And that's what we'll focus on today. But I'll also speak to, can models adapt to defend against these kind of adversarial shifts? So let's begin with natural shifts. I'm going to talk today about a method that I call TENT for fully test time adaptation by entropy minimization. So TENT is a method that helps a model adapt itself in changing conditions, like types of weather, for instance, by actually updating the model on the new and different data as it appears during testing, right? And this is going to be done without altering training. We just have the model as it is in deployment, and it's not going to require more supervision. We're not going to have more labels. We're not going to have a human intervene. This is an update the model will do on its own. And this was work I did while at Adobe in collaboration with Berkeley AI Research. I'm now at DeepMind and continuing this kind of work. So, right, this fully test time adaptation problem, its purpose is that, like I've said, we want to adapt to these natural shifts. Why? Because when this shift happens, our error goes up. And it's this shift between our source data, right, what we trained on, where we have lots of data potentially, and our target data, the test data that we want to deploy to. And I have some more examples of shift here. There's the corruptions I already showed you with types of noise and blur. There also might be simulation to real shift. Like you can see these 3D models of horses, or this video game, where of course we want to deploy our models on actual real images, whether of farm scenes or in cities. Or just for the purpose of benchmarking and understanding and research, we might have simpler data sets where we look at, say, digits, these numbers. We might have numbers taken from photos of houses, that's above the Street View House data set, or we might have handwritten digits, as we have above. There are all these sorts of shifts, and while there's change, this change is in the input, right? The task is staying the same. By that I mean, we're still trying to recognize birds, just what a bird looks like has changed. We're not doing something where what the model does entirely changes. Like on one day you care about cars, and the next day you care about boats instead. That's not the kind of shift I'm talking about. So I already outlined the need to change, but why specifically do we want to adapt during testing, right? Of course there's the error. Of course fixing our errors is maybe enough, but the reason for testing is that we don't know the ways the data might change this way, right? It's hard to anticipate all the possible ways data could change. But if we just accept the test data as it comes, well, now we know the problem we need to solve, right? We have the data. We can try to improve on that data. But why not try to train better for this? I argue for this fully test time setting for some just practical reasons, right? One is just availability. Like we might have a model and not have all of its training data, right? If you have an image classifier trained on a data set like ImageNet, that's hundreds of gigabytes you might not want to put on a mobile phone when you deploy your model. We might just only have the model itself. There's also efficiency, right? If I want to update on a day with this orange weather, this strange Californian wildfires, I don't want to have to reprocess all of my data before I can make a prediction, right? You want your phone to work immediately, or you want your car to steer itself without saying, oh, please just wait an hour while I relearn everything from scratch, right? And finally, there's accuracy, as I've already highlighted here. Our model might just not work well enough without adapting. So these are all the reasons we need to adapt during testing. So let's now look at how we might approach this, right? If I'm going to be adapting a model, if I'm going to have updates to the model, I need some sort of loss to determine what those updates are. So our basic approach is to consider the certainty of the model. How confident is it? And we're going to use this certainty to supervise what it learns. So what do I mean by certainty? If you look on the right here, there are these bar charts. So for each bar, that is a class, right? We have a classifier saying doing dogs, cats, birds, people, etc. On the left is a high entropy, low certainty prediction, right? Because the probability of each class is basically equal, right? That's no certainty. On the right, we have a high certainty, low entropy prediction. Why is it low entropy? Because see, now there's this peak. There's one bar, meaning one particular class that the model is confident in. Why am I caring about confidence? Well, if we look at this histogram on the left, what we're measuring is the error in y, right? How wrong the model is, and the entropy in x. In this case, normalized so that the least confident is 1, right? The highest entropy. And the most confident, the lowest entropy, is 0. And what you see is on the far left here, that the error rate is the smallest for the most confident predictions, right? And as we go to the right, the entropy goes up, the model is less confident, and it also makes more errors. So this is just a signal that maybe just how confident the model is could actually be used for adjusting it. Because if we could make it more confident on the data to look at it in a different way, perhaps that might also reduce the error, right? It's not guaranteed, but this is our motivation that we're going to check. Is this clear in terms of what we're measuring? Are there any questions about entropy or model predictions before we go on? Because we're going to use this throughout the talk. Happy if there are. Great, well, let's continue. So another way to look at this issue of entropy and error is now we can plot, again, on x is entropy, how uncertain the model is, with it being more uncertain to the right. And now the y-axis, L, is the total amount of loss. But now each point isn't a single image, it's actually an entire data set. And what we're looking at is what is the loss and what is the uncertainty over that whole data set, where the colors tell you what kind of corruption there is, right? So these red points are all data sets that have been corrupted by different noises, like Gaussian noise or impulse noise. And the blue points are corrupted by blurs. So what we see here is that for our model, this is just our normal trained model so far, we're not adapting it yet. In general, as entropy goes up as we go to the right, the loss does also go up as we go to the top. And it might be subtle on this projector, but there are points that are brighter colors. Those are the more extreme corruptions. There's different levels. We could have a little bit of blur or a lot of blur. And as you get more severely corrupted, you see both more loss and more entropy. So again, these seem to be related. And we can use entropy as some sort of measure of how much shift there is in the data, right? Because that's a problem in itself. The data may change, but how do you know? If you don't have labels to check how the model is doing, you might not even know that you're making more errors now. There's one key point I want to point out, which in the bottom left of this plot, one of the points is black. So that's uncorrupted. That's just normal testing data, the same kind of data in training. And we see that in that case, both the loss and the entropy are very low, right? Because we trained it to know what to do on that data. So again, that shows that entropy makes sense both on shifted and unshifted data. So now what are we actually going to do about it? Okay, our method in a nutshell is to minimize this entropy of the predictions, right? We're gonna optimize for the model to be confident with two steps. One is updating the statistics, which I'll show you what I mean by that, and also updating just a few parameters. And that's where we get the name of our method, TENT, for test entropy minimization. And so if we look at this train and test plot, standard training, what does it do? It optimizes our model parameters theta, the theta in red here, right? We have some loss that given a prediction y and a truth y, looks at their difference, updates all our model parameters theta. Where now at testing, our method tent is gonna optimize what I'll call a modulation, really just a change, delta, that will be some difference on our parameters. Not to minimize the supervised loss, because we don't have labels in testing, but just to minimize that entropy, like I showed you on the prior plot. So again, this method won't alter training. If you give me a model, if you give me a classifier, I can try to adapt it this way without knowing what optimizer you used, without knowing how large your data set was. I don't need any of this. I can just update the model as it comes. And the way it will do this is online and batch by batch. I mean by this, a batch of test data comes in, say your model's on a server, there's a certain number of uploads, you want to run it. We're going to look at that batch, make a prediction, update the model, and go on to the next batch. There's not a big waiting cycle of training again between predictions. We just predict and update, predict and update. So let's look at this update in more detail. So, right, I say updating statistics and just a few parameters. What do I mean by that exactly? So the statistics are in a normalization layer, right? If you're familiar with, say, batch normalization or group normalization, the first steps are that we have some mean, mu, and some variance, sigma squared, and we subtract out that mean and divide by the variance, right? That's what we mean by normalization, just trying to get the features in a standardized range. But there's a key separate step to normalization layers, which is transformation, right? After having subtracted the mean and dividing with the variance, they also multiply by a scale and add a shift, that's scale gamma and shift beta. And these scales and shifts exist for every channel, right? In our networks, we have many different filters, many different channels. And what this layer can do is separately scale and shift each one. So there's something interesting to express here. What we will do is we'll update these normalization statistics, the mean and variance, on the test data rather than the training data. Normally, we collect it all during training, but this is one simple step we can take to say if the test data has changed, it might have a different mean and variance. So let's update that as we do a forward pass of our network. Then in our next step, having made a prediction, right, we can measure the entropy of it. Entropy is just a function of the predictions themselves, right? The high probabilities and the low probabilities. We don't need a label for that. So we can calculate entropy and then take the gradient of it, right? Just as we normally optimize a deep network. This is now we're taking a gradient during testing. And out of all the parameters, just these scale and shift parameters. And so you may have seen this in some prior work on what's called film, right? Where this is depicting if you have a activation coming in at the bottom, you could first scale each channel, making it larger or smaller, and then shift it, just adding or subtracting from it. So prior work learned this kind of modulation, but during the training, right? Everything I'm talking about is doing it during testing, which indeed does make it different. And the other aspect is that we can do this during testing because we're updating less than 1% of the total model parameters, right? So you can do this too. This is a very efficient, interesting kind of experiment, because on a single GPU, you might take a massive model that took days or weeks to train, but to adapt it could take less time. So it's also the excitement of this research area to me, because we can really analyze what's happening as we use models and try to make them better. So right, how does it actually do in detail? Let's look at some results finally. I showed you these corruptions with the different types. Now on the x-axis, right, we have Gaussian noise, shot noise, fog, weather, like JPEG compression. And so every bar here is a method, where black is just our source model, our normal trained model, right? What I first want to point out is all the way on the left, there's just the original data, right? This is the data the model's supposed to be good at. And we see the error is least there. What's very important is these test time methods, tent in particular in blue, doesn't do any harm on normal data, right? If you want something that's supposed to adapt, it would be a very dangerous, risky kind of adaptation if it went wrong when nothing changed, right? I feel like this is the bare minimum we need, right? Don't do any harm. Then let's see if we can help. So if we look at these other bars, in every case, the error after adaptation, so going from black to blue, is lower. And methods that don't actually update the parameters, like norm in this case, just updates the statistics, the means and variances. Without updating the scale and shift parameters, we don't see as much improvement. This gray bar was the most sophisticated training time method at the time that we first published our method. It's called adversarial noise training. And it tries to come up with, on its own, all different possible corruptions during training, right? And it tries to reduce error for all of them. But the problem is, those guesses at corruptions might not be like the real ones, right? This is the reason why we actually want to adapt during testing instead, because we can adapt to the data we actually get instead of the data we might have. And while that was state-of-the-art when we did it, actually the state-of-the-art is advanced, right? That's what the state-of-the-art does. But in fact, the current state-of-the-art are also these kind of test time adaptation methods, extensions of tent. So there is more to be done in this direction and things to explore. But let's first look at more experiments. I showed you corruptions, but there's other kinds of shifts, right? We can look at these digits. We can look at training on simulated data, because we can make a lot of simulated data, maybe more than we can collect real data, and do some analysis of what these updates are doing and how it works on other kinds of models. So our baselines for the rest of this are going to be, as we already saw, just this source-only unadapted model, right? Just the model we have trained. We're also going to look at domain adaptation models. This family of models uses your training data, your source data, at the same time as your target data, the testing data, right? So our method only needs that target data. The reason that's a useful difference is you might not still have the source data, right? But domain adaptation uses both. That existed before. Let's see how we compare it to that, because when it's using strictly more information, maybe it could do better. There's a very interesting method in yellow here, test time training, which also updates the model during testing, but does so in a different way that I'll explain in a moment. And last, these methods in blue, like tent, are fully test time. Like we could just update the normalization and not update the parameters. That's test time normalization. Or rather than just have this gradients softly of entropy, we could instead do pseudo-labeling, where for each prediction, we look at the most probable class, right, what the model thinks it is, and just pretend that's the truth. Treat it like a ground truth, and do supervised learning on our own predictions. That's kind of a hard version of our tent method. So I mentioned test time training. It also updates during testing. How does this work? Rather than using entropy, which is kind of built into our model, right, because it has to make predictions, so we can measure those, you could try to add a separate task. So self-supervision is when we design some learning task where we can make our own labels, right? I'm showing an example here on the left. We have an image of a bird, and we could, for instance, rotate it. right? We could look at these 4 different rotations at 0 degrees, 90 degrees, etc. And we know what angle we rotated the image to, right? That's a task where we know the answer. We can make our own answer. So we could try to optimize for this, right? Where we have some parameters, theta e, for our embedding, what is our feature, and some parameters for our self-supervised prediction, right? Which is the rotation. So test time training first learns this kind of task jointly with a classifier, right? So at training time, given an image, it's going to optimize for, is it a bird or not, right? The supervised problem with labels, while also simultaneously optimizing for the self-supervised problem. How is it rotated? The reason they do this jointly is that then later at testing, we're not going to have the answer if it's a bird or not, right? We have to make our own prediction. But we can still do our self-supervised task. We can take updates of this rotation problem while our supervised parameters are locked, right? So this is a kind of updating during testing, but one where we had to do some preparation, right? We had to change how training worked. So this isn't fully test time in the way that I've tried to motivate, but still it's related, it's sensible. Let's see how it can do. Right, so I showed you corruptions on ImageNet because that's a larger scale data set, more representative of what we want to do. But here we'll look at CFAR, a smaller data set, just for the sake of comparison. So our source method gets a certain accuracy, right? Or error, sorry, a certain error. And these corrupted errors are much higher than the reference. So on normal CFAR 10, the error is 5%. On corrupted CFAR 10, it's over 40. Now, if we do domain adaptation, these are the methods that use the source and the target data during training, then we're able to reduce that error, right? That's good, but we needed all of the data and many, many updates, right? Tens of thousands or hundreds of thousands of updates. If we look instead at test time training, it's also able to do well. It's reducing error, but now while it needed the source data to train on, during the testing, it only needs the target data, right? So now we've reduced the amount of data, but we still had to do some setup steps to get there. Finally, if we look at the fully test time methods, these are actually able to reduce the error the same amount or more than the domain adaptation methods, right? RG and UDASS. This is interesting because that in some way has even more data, right? It gets to look at normal data and shifted data at the same time. You might expect it to do better. But if you think about it again, that's also a harder task. You're saying, I want a model that works on normal data and corrupted data. Those are, in some ways, 2 different tasks. Maybe your one model isn't enough model for that. Whereas if you think about Tent, we first train on normal data, however it was trained. But now during testing, we're going to specialize to exactly that testing data, right? The model can fully concentrate on that. And indeed, in this case, that allows the model to do better while still only using testing data. Last, I want to point out, this was all using the test data, right? But if we collected even more corrupted data, Tent continues to improve. So by using more points, we go from having 37% error down to 34, because this is a kind of learning at test time, right? So now let's look at digits, right? Here's an example again in the corner of we have maybe just house numbers, right? People taking photos of addresses versus handwriting and other styles. Again, source gives us a certain error rate. And then if we do domain adaptation, we can reduce that. Things can improve. We get lower error. And here I'm looking at not just which data is used, source and target during training, but how many epochs of updates there are, right? Like how many updates I need to take. In terms of epochs, where an epoch is one whole pass of the data set, right? So this is not a quick process to do. And we see for domain adaptation, because it's using both source and target, it's 10 plus 10, because it's 10 over test and 10 over train at the same time. Whereas if we consider batch norm intent, these don't need any further updates on source. They've already learned that, right? And we don't even have the source data anymore. So in a single epoch on target, we're able to comparably reduce the error on 2 out of the 3 data sets. We're not as good at one of them, as you can see in the middle, but 2 out of 3 cases isn't so bad. And if we continue to update with Tent, so instead of a single epoch just going through the data set once, we could go through a few times, we're able to further reduce that error. Again, we're doing this without any further information, right? All we have is the test data and the model, but we're able to extract a better model from it by updating on that data. So Tent can improve over domain adaptation in 2/3 of these cases without the joint use of that data. And this also is more computationally efficient, right? Because we're using less than 100th of the data, because in this case, the test set is smaller than the training set, and 1/10 of the optimization, because we're making fewer gradient updates in doing so. Lastly, I want to point out that these results are for what's called offline adaptation and optimization, right? We look through the whole test set once, we go through it, make all our updates, and then we can predict again if we still have the data, right? But if you think about it, that's not so realistic. We can't just store unlimited amounts of data. It would be better to just work online, make a prediction, update, and move on, and keep going without keeping the data, right? So that's what I'll call online adaptation. And those are these results highlighted in red of tent in one epoch offline gets 10% error. It's 12% online, right? Where online is actually possible and practical. So we're not losing that much by being more real in this case, although we could do better if you could hold on to more of your data. So this truly is a fully test time method because all we're using is test data as it comes in. So right, that was looking at these digits. Let's look at now simulated data. In this case, there's a standard data set called VisDAC, where you train synthetically and then test in the real world. This is a bit of maybe an extreme shift, more extreme than you would try, but it is still interesting to measure. So here the task is classifying images. We're working on simulated data versus real data, and the metric is again just error rate, right? The error percentage. For our results, the source model has a certain error as always, in this case 56. Tent, with its affine modulation, brings that down to 45. That's updating those scales and shifts. That's an affine update. Whereas if we update all of the parameters now, because this shift is more extreme, we can minimize the error even further. But you'll see this is all with a star. That star is very important. We're updating all of the parameters except for the final layers, the ones at the output that have no more normalization. Because we're minimizing entropy, if we just arbitrarily update the network, right, that last layer, we can make the entropy go down without helping the model at all, right? Because entropy is about confidence. If I just say, took all my predictions and multiplied them by a very large number, they'd be in the same order, right? The most probable class would be the most probable, but it would be even more confident than ever. The entropy would go down, but no prediction would change. That's not helpful. We have to keep the optimizer from finding that solution. So we update all but the last parameters. Exactly. And so this parameterization does matter. Like harder or stronger shifts might need more parameters to optimize. And that's still, a more open problem to continue researching and developing. Let's look at another simulation case, right? People have tried to train or co-train driving models on simulated data, because of course that's safe. It doesn't matter if your computer crashes as much as if your car crashes in real life, right? But there's a shift. This data is obviously different, right? In this case, we're looking at a video game, GTA, in the top left, and actual real cities in Germany, cityscapes on the bottom left. So here the problem is actually semantic segmentation. You see the prediction and annotation on the right. We want to know every pixel now, not just what's in the image. Just saying street is not enough. We need to know where the street is. So here the metric is intersection over union, where higher is better, unlike all the error rates I showed you before. So again, we have a source model of a certain intersection over union. Think of it like accuracy, pretty low, 28%. By just updating the normalization, we can get up to 31%, and with tent, we get up to 35. What's interesting here is that we can do this same experiment just per image, right? I said that tent uses batches. We take a whole batch of updates, sorry, a batch of inputs. But that's because it needs multiple predictions. For a classifier, that's one per image. For this segmentation problem, I have a prediction per pixel. I can treat a whole image as many batches. And so I can actually adapt to a single image at a time and move on to the next one and still reduce error, which is perhaps even more online than needing a batch. So that's what we get for the simulated data. Let's look at actually what this looks like more in particular, right? So this is that single image setting I told you about. So we get this image in the top left that comes in. Notice there's a motorcycle driver inside it. If we look at the truth, the little person in red on top of the motorcycle in blue. Our initial prediction of an unadapted model doesn't even know there's a person in this scene, which doesn't seem particularly safe if we're going to make a decision based on that. After the update, we've actually recovered the presence of this motorcycle driver. There's still many errors in the segmentation. I wouldn't have this drive a car yet, right? This is just the research phase, but we've at least recovered more of the classes that are in the scene and have some prediction of where they are. So we can see this step by step because tent iterates, right? It makes steps as it goes. And so you can see this improvement from our initial prediction, not even having a person, to finally having a person here and having a better idea of where they are. This is all being done in a single image, not on the whole data set. We're specializing the model as we go, step by step, and improving the results. So that was simulation to real, but I told you about this Bay Area story, right? Our very odd weather we had that time with the fires. Can this help here? We're just going to look at this qualitatively because I didn't spend 2 hours to annotate every pixel, but you can still see what's happening for yourself. So here we have an unadapted model trained on street scenes, and some of this is maybe right, but let's see what happens when we adapt it. If we just add the normalization, the cars are more clear now in blue. If we further do entropy minimization, we're getting things like some of the street signs in yellow also. And so while there are errors, the sky is certainly not a building, but its orange color is still confusing our model. We have now many of the trees. We have a better idea of where the street is, where the sidewalk is, and sharper outlines of the cars. Again, not because we collected wildfire data and labeled it, but because our model was able to update itself and get this more correct. So I showed this for some standard architectures like residual networks, either for classification or segmentation. But of course, there are new architectures all the time. In particular, there's more and more with self-attention. The self-attention net on the left is one particular form that I won't go in the architecture in too much detail. But the point is, rather than doing convolution, it actually does a kind of attention, right? A pairwise operation over many of the points. And on the right is what's known as an equilibrium model that rather than having many layers in a deep network, each one with its own parameters that it runs from beginning to end, it actually has a single layer with the same parameters that it runs over and over, solving an optimization problem. So it's a very different type of network, right? But we can see, can we still adapt these with this tent method? And indeed, we can. If we compare the source model without adaptation to adaptation by normalization or tent, in every case, tent is achieving the least error, even on these more exotic models, which are architectures that weren't out there while we were developing the method, right? So tent is quite general in this way of as long as there is this kind of scale and shift, this kind of normalization in your network, we can try to adapt it by tent. We don't have to redesign our architectures to adapt them. We can adapt what we have. So to now analyze this a bit better, because I've shown you the real results and how error can go down, let's look at how the loss and the entropy relate once more. Where in this plot, we're actually looking at changes. That's the delta L for the change in loss, and delta H for the change in entropy. So the very center of this plot is what would happen if our updates didn't change anything at all, right? The loss doesn't change, the entropy doesn't change. As we go to the right, the entropy is increasing, and as we go up, the loss is increasing, right? So what we'd like to see, most of all, is for the loss to go down, right? We want points to go down. Now, what's being plotted here is actually every point in this plot is a single data point over many corrupted test sets. So we're looking at for every point, how does tent change what the model predicts about it? And so while you see many things do happen, there's points all over this plot, entropy mostly goes down. There's more dark points on the left than the right. And there's this diagonal to it, right? Where there's a tendency to become more confident and have less loss, right? That's what we want to see. And we in fact do see that. And this is related. We can do a statistical test for this, measuring what's called the rank correlation. And here we're getting 0.2. That's not the strongest correlation in the book, but it's a lot more than 0. And importantly, it's not negative. So this is showing that our hope that entropy could relate to error is turning out to be valid and true when we empirically check it on these kinds of shifts. Right, so to summarize this setting and what we've done, while you could try to update a model given supervision, right, something like fine-tuning, you have target data. If you can collect labels on it, right, the labels Y, sure, go ahead. Train with a loss of the data and the labels and update it. But of course, collecting that target data is expensive, and labeling it is even more expensive. For adaptation, if you still have your source data, and maybe you collect target data, you get the target x's, xt, but you don't have time for labels, sure, you could do a loss that is supervised on source using xs, the source data, and ys, the source labels, and only xt, the target data. Great, but again, that's not going to be test time. That's going to take a long time. So test time training was one step toward this, right, where they jointly train across their self-supervised task and their source data. And now they have a test loss for the first time. So this is a kind of test time update, but it's not fully test time, as we've motivated, where we use no source data in our updates. We only have target data, and that data has no labels, right? We just update with a test loss on the target data as we have it. So of all these types of data and labels, fully test time adaptation only needs the target data X and the model, which is the only thing you have in deployment. So that's important. So right, to summarize, Tent can help adapt in these different settings, but there are many next steps to take, right? We can update not just our models, but our own understanding by exploring more losses, right? Entropy is a very simple loss, but it isn't always stable, right? There could be shifts where it converges to something that isn't an improvement. So we might need alternative losses or ways to optimize that would be even more reliable. And as I showed, there are more parameters to choose. We focused on these scales and shifts with some updates that were using more parameters, but different architectures might need different choices, right? Like large vision transformers perhaps need a different way to adapt. And last, there are always more shifts, right? There are the benchmarks I showed, but more shifts are happening all the time. And very importantly, some of them are even real shifts taken from data sets in the wild, like the WILDS data set from Stanford, where you could imagine, say, data from different hospitals that is looking at the same tissues, but needs to work across these different places it was collected. Tent can work on that one. I've done the experiment, but the question is, what about even more shifts, right? There are things to check here and a lot more to be done. So having looked at natural shifts, I'm going to now get into adversarial shifts, what we can do with attacks. But are there first any questions people have about the natural shift case? I'm also happy to take questions at the end, but please.
My question is adaptation of only one image. What happens in that case? So what is...
Sure. So to repeat the question for the recording, the question is, what happens if there's only one image? Could we adapt to a single data point? So it depends on the task, right? For an image classifier, where we're making just one prediction on one image, Tent doesn't work because there's nothing really to change. You can just become more confident in that single prediction without changing it. Test time training with this auxiliary loss, the rotations, can work on a single image by augmenting it many times and basically trying to come up with a batch and updating. But the thing is, when you do have a batch, Tent reduces the error much more than test time training. So there's kind of a trade-off of when you can use one or the other. This data augmentation trick, taking a single image, augmenting it into many similar images, you could apply something like Tent to that, right? Be confident across all the transformations. That's a method called memo that can help also, but it doesn't help as much as Tent over a batch, and it takes more time, right? Tent makes a prediction and update once for every image in our batch, where memo first makes a batch of one image. So say you made 30 augmentations of the image, now it takes 30 times as much time to make that single prediction. So how to more efficiently work on a single input and more effectively is an important thing to get to, again, depending on the task. For segmentation, that result I showed you with the smoke or simulation to real, that is adapting to a single image. It's just a single image of many pixels and many predictions. Yes. Okay, I'll take one more and then we're going to move to the next topic. Yes?
On the topic, so can't you just create a lot of images out of one image and then do the adaptation that way?
Yes, that's what some of the methods are trying to do. It's just then that takes more...
For your method. And the other question, that have you explored like what is the optimal data set? Because like in production, maybe if you want to use this, then you need to wait for some requests.
Yep. Sure. So the follow-up question is, if we do need batches, how large a batch do we need, or how does it vary with the batch size? Because in production, we don't want to wait too long. The amount of error reduction, the amount of improvement, does depend on batch size, but it reliably does reduce the error across a variety of them. I think the minimum size on like ImageNet size scale data we've looked at is, I think at 16 or 32, it still improves, but it improves more at 64. But if you have more computation, you can scale out and on a single image, make a batch of its augmentations and update on that with our method as well. And that can improve. It just doesn't improve as much as if you have a real batch. So thank you for those questions. Now I'm going to move on briefly to the adversarial case. Everything I showed was for natural shifts, right? Things like the weather. Now we're going to look at what if an attacker is actually specifically trying to make our model wrong, right? Is there a way we might adapt to this and better defend our model? As other talks at DataFest have talked about adversarial robustness. So this is a project I completed at DeepMind with collaborators both in university. Francesco Croce is a student in Tübingen, and also industry with collaborators at DeepMind, Sven Gowal, Thomas Brunner at Everywhere Robotics, also part of Alphabet, and the advisor Matthias Hein, and Taelan from DeepMind. So we're going to look at, there are these adaptive methods, like I showed you for natural shifts. We could try to adapt as a defense, but are we there yet? Do we adapt enough? Can it actually work? So what I'm going to go over now is first, what do I mean by a test time or adaptive defense, as opposed to just a model? Briefly overview a case study we did to categorize such adaptive defenses and also measure them, where we actually find that their robustness, how strong they are against attacks, is much less than the papers claim. The papers tried to measure them, but because they're new and they change, that makes them a bit more complicated to measure correctly. We find that by measuring them a little more intensely, they're not as robust. And last, some recommendations of how we could better measure or perhaps improve these defenses. In case you haven't seen attacks, I just want to really briefly outline this whole field, really, which is that these deep nets that we have, our classifiers, are vulnerable to attack, meaning a kind of perturbation, right? If we have our input X, a normal image, our usual classifier will be pretty sure it's a cat, right? Deep learning does work more than not in this day and age. But if an attacker crafts a certain perturbation, here it looks a bit like noise, that it can add to the input, it can make it wrong, and very wrong, right? Like now our model's not only thinking that it's guacamole, it's thinking that very confidently. So there's a problem. Train time defenses try to make new model architectures, losses, or optimizations that when training a classifier, so-called adversarial training, help deal with this problem, right? So that it's not as affected by perturbations. But these don't change during testing, right? So if the attacks do keep changing, maybe that training won't remain as robust. That's the potential problem. Whereas test time defenses will alter the inference during testing, right? Maybe they'll change the input to prevent the attack. Maybe they'll even change the model. But while they're test time, they don't adapt in the same way that Tent adapted, right? Because the changes that Tent made depend on the input, right? It's changing some part in response to what the data is. Test time defenses are more things like randomization that maybe change, but based on flipping a coin, not based on what's actually in the image. So what I mean by adaptive test time defenses are those that do alter the inference, right? They alter the predictions by conditioning on the input, by re-optimizing that input or the model, right? And this iterative kind of update during inference tries to improve the robustness, meaning it tries to prevent attacks from making the model wrong. The potential benefits are that we might still have as good a model on the clean data, right? Clean data meaning data without attacks. Because a side effect of existing defenses is that they can often make the model more robust against attack, right? Less errors on attack, but actually on normal data, because hopefully the whole world isn't attacking all of the time, the models are actually less accurate. It's this trade-off, more robustness for less accuracy. But if we're changing at test time, maybe we could keep the accuracy and also boost robustness. That's the hope. And so part of the reason for looking at this is, as I just showed you with Tent, test time adaptation can improve on natural shifts. So why not adversarial shifts? Let's investigate. So there are two main schemes for in adaptation in the context of defense, right? We have input adaptation, also called purification, right? Where we have some process, some iteration that will change our input before it's given to the model, right? We could also look at model adaptation, or this kind of test time training scheme, as Tent did, right? Where we actually update the parameters or the latents, the activations of the model, where both are iterative, right? We're going to take a step, look at the input, update the model or input, take a step again until we're done. So to illustrate this better, we're going to look at some different building blocks of such adaptive defenses one by one. The first and universal property is that they iterate, as I said, right? We might have some gradient, some loss function L, and we take a gradient with respect to the input X to update it. Or we might have an update that comes out of a model, right? Given an input X, we'll have some model G that says how to change that input to try to remove the attack from it, for instance. In that kind of scheme, that means we have some auxiliary network, right? We're equipping our model, our classifier, with some other network that'll either, say, define a loss or directly make an update. So on the left, we see, for instance, our input goes into the auxiliary model in green and just outputs a new input, right? That then goes into our classifier C. That's one way to do it, where just directly the model changes the input at test time. Another way on the right could be that actually our input goes into a model that looks at the input and defines a loss on it. So we can take an update and go from there. So there's different ways we can use auxiliary networks, but the main point is there's some network other than our classifier that gets involved. And I mentioned randomization. This can be either explicit, where here in this image of a leopard, we're adding noise to it, because perhaps this noise will drown out the noise from an attack, right? That might be one way to try to defend. But it could also be implicit. If we have a model that depends on the whole batch, right, the way that we group our data together, rather than a single point, then the way that we batch our data together, like if we have all the data, the blue points on the left, we could select different batches from it, different subsets of the points, we might change the prediction. This could be part of our defense. And last, we might just use more data, right? Rather than just relying on a test input that could be good or bad, right, clean or attacked, we could have our own reserve, our own private inputs that we know to be clean, we know to be good, and then try to use these together to have more robust predictions. So these building blocks all exist. We can look at a whole suite of defenses that use these different elements, right? As we see in the dots here. They're quite recent. They're all from 2020 to 2022. They use different building blocks and they use different principles, but they're all attempting to be more robust by adapting, right? What we see is that we'll need different methods to attack each one. I don't have time to go through the specifics of each attack, but the point is that we need several, but there are recurring ones. There's common elements to each of these attacks. So we can find a common toolkit that'll let us evaluate them. But the main thing is, how well do they do, right? There's some reported robustness from every paper, and then there's our own robustness when we've evaluated them with this common toolkit of pieces to let us counteract adaptation. And in every case, we see that the robustness is reduced. In some cases, quite strongly, right? Say 53 points. And even worse, for 4 of these methods, they actually hurt. If you start from a robust model from adversarial training and try to make it even more robust by adding these kinds of adaptation that I briefly showed you, well, a strong enough attacker can turn the adaptation in the wrong direction, where now the model actually updates not to be more robust, but less, because in a way, you've given the attacker more to change. If the attacker can only change the input and your model doesn't adapt, it can only go so far. But now, if your model or input adapt, if they pick the right attack, they might make the updates go in the wrong direction. And that's what we see for 4 of these defenses. And there is one, ADP, that gets a little medal for giving the highest gain, but this gain is only on top of a standard model, a non-robust model. This 0 in the last right column is the robust accuracy without adaptation, right? The 0 means this is totally not robust. This is a model completely open to attack unless it adapts. by adapting, we can get that robustness up to 33%, but that's still quite a poor model. So maybe that's not ready to use, even though it's more robust. And aside from the accuracy, how well these defenses are working, we can look at the time, and it is slow, right? Each of these snails on the right is a method that's more than 10 times slower than not adapting, right? The static model is much faster. In the worst case, it's more than 500 times slower. So if these were giving a lot more robustness, that might be something. You're making a trade-off between computation and defense. That would be useful. But in this case, as we've seen, we haven't yet actually found an adaptation that can indeed help, right? So that's a negative result at the moment, but what we can hope for is some way to use this amount of computation in the future against an attacker, right? Maybe your defense is 10 times slower, but if that made the attacker's job 1,000 times slower, that could be worth it, because maybe they don't have enough computation to actually mount that attack. But we're not in that regime yet. That's something to further pursue in this kind of adaptation research direction. So right, to summarize, these are more complex defenses. They're more complicated to evaluate. It's not that the prior papers were wrong. They used the tools they had, just more effort and attention were needed. There isn't a single attack that works against all these adaptation methods, but there are a few combinations of techniques that let us do this. We don't need totally new attacks. We can just recombine what we have. And the adaptive test time defenses that build on top of a robust model, right? We'd like these to combine. A static robust model with an adaptive defense could be even more robust, actually don't improve at all. There's no improvement. And they can even degrade that robustness. And adaptive test time defenses on top of a nominal model, one that isn't already robust, can give some robustness, but less than if you just adversarially train them. So we're not making progress on this front just yet. And while test time adaptation changes things, it increases the time by even multiplicative factors, right? Or even orders of magnitude, 10x the time or 100x the time. So there is this negative result of not being there yet, but there's still enthusiasm about it, right? And we might figure it out. So the latest defenses do keep trying to adapt. Here I'm just highlighting two methods from ICML 2022, just months ago, that likewise try to adapt the input or model. And so we need to continue checking and trying to see if adaptation can help against adversarial shift as well, because the rest of the community is investigating this kind of thing now. So right, is this really the last step on this research direction? I'd argue certainly not. We've just taken a few first steps toward adapting at test time, showing how we could make some updates. But I hope I've caught your interest and that you might join us in taking the next steps. Thank you very much. I'm happy to take questions.
And before that, I will ask the first question. So, what was the difference between the BN method for the first part of your presentation and your method? Like both are trying to adapt the questions, right?
So the question is a very good question. What is the difference between just updating the normalization, the BN method, and our full method tent? And so the key is that there's actually two parts to a normalization layer. There's the actual normalization, right? Subtracting the mean and dividing the variance using the statistics. But there's a second step, the transformation step, where having normalized the features, we then transform them with a scale and a shift, right? So in BN, it's just updating the statistics during forward. It collects a new mean and variance, but it does not change the scale and shift parameters, which are the learned parameters. Where tent, it calculates the entropy of the prediction, and then it takes a gradient to update the scale and shift, right? So even though we call them normalization layers, actually they have normalization stats and one step, and then they have the transformation parameters as the second step. So tent does both steps. Thanks for the question.
Yeah, I see. So it means that the BN, the smaller version, it does not even use the loss to update. Like
no, it doesn't use the prediction at all. It's totally bottom up. It's just a function of the input. It's not a function of the output like tent is. Yeah.
So one more follow-up question on what was asked before. So when you are working on a segmentation problem, and I can imagine that you have like lots of outputs in a segmentation problem, and that's that a single image adaptation kind of works, right? But like
Right.
In implementation, is it still one inference?
It's a single forward pass. So in semantic segmentation, again, this is the task of making a prediction at every pixel, right? It's pixel-wise classification. One image is very many pixels, right? So the way tent works in this case is we do a single forward pass, right, making a prediction at every pixel, and then we can update our statistics based on that image, the first step, right, the means and the variances, and then we can take the entropy at every pixel, everywhere we have a prediction, take a gradient now that's another single backward pass through the network. So tent always just makes one forward, one backward pass, whether it's segmentation with pixel-wise predictions or whether it's image classification with image-wise predictions.
I see. So that because of the fact that your entropy is the loss that you measure for the segmentation case is like an average of many entropies, it
That's right.
has a better effect.
Yeah, just like in a batch of images, our loss is the entropy across each image. We take a gradient of all of those. So the parameters are the same across a batch, to clarify. Maybe this is helpful. When we have a batch of images for a classifier, we say have 10 images, we have 10 predictions. We're still going to only have one set of parameters. It's just the value of those parameters now depend on that batch, but we share them across. The same for an image. We only have one set of parameters, the parameters for that image, but we're going to update it based on all the pixels. But like a pixel in one corner isn't going to have different parameters than the pixel in the other corner. Every pixel in that image is going to use the same parameters that will be updated as a function of all of them.
Thank you. I have many more questions, but our sessions are starting. So let's thank Evan again.
Thank you for coming.